Hello, my name is Junyoung Meng, the presenter of Deep Learning class assignment. In this presentation, I will talk about my research topic, extending medical transformer to modality generical model. My goal is to extend existing model named medical transformer, which trains unlabeled 3D medical images with self-supervised learning manners to multimodality. The order of presentation is as follows. Medical image analysis have achieved remarkable progress with the use of deep learning for the past few years. However, building a large dataset for training deep learning models is challenging in the field of medical imaging. The main reason of the problem are the difficulty of data acquisition and annotation. Not only does medical image annotation requires a lot of labor and time costs, but also requires expert annotation by trained physicians who are difficult to be recruited in large scale. In real-world practice, it is usually impossible to collect extensive samples from a single clinical center. For the transfer learning in medical imaging, the standard approach was to pre-train the existing 2D-based neural architectures. After pre-training, fine-tune the model on small-sized medical imaging data. This approach yields better performance than the random initial-based training strategy. However, problem happens when using transfer learning mechanisms pre-trained from 2D natural dataset to 3D medical dataset. 3D volume data was split into 2D slices from 3 planes and pre-trained by 2D models without recovering to 3D form representations. This method caused a problem that disregarding rich 3D spatial anatomical information, thereby inevitably compromising the performance. Considering this problem, some other studies transfer from 3D publicly available models pre-trained on the natural video recognition dataset. However, these methods have not yielded the desirable result due to the comparatively large difference between video and 3D medical data. In the case of 3D medical data, all scans are registered, resulting into sophisticated yet recurrent patterns. Learning a 3D medical image network transferred from natural screen video without considering this characteristic leads to a strong bias in medical imaging analysis. Thus, it motivates the need to learn a source model from transfer learning by directly utilizing the medical imaging dataset, capable of learning subtle difference among medical datasets. To build a source model directly from 3D medical volume data, recent works pre-trained their models for target tasks such as brain parsing and organ segmentation over labeled dataset. 3D Math built a large-scale dataset from a collection of 8 annotated medical datasets and pre-trained the 3D residual network for the segmentation task. Although this fully supervised approach may yield more powerful target models, they demanded a volume of annotation effort to obtain the source model. A generic framework is to first employ predefined proxy tasks to learn feature representations, capturing the data characteristics via self-supervision, and further fine-tune the target model with a handful of task-specific annotated data. I will introduce 4 examples that adapted self-supervised learning in medical image. The first one is a paper from Chededal posted at 2019. They simply used autoencoder framework and used image restoration as a proxy task. Second one is Rubik's Cube, which posted in 2019. They separated 3D medical image in 8 3D patches, and they used rearrangement and random rotation as proxy task. The third one is Taleb et al.'s paper, which posted in 2020. They transformed existing 2D-based self-supervised methods to 3D form. According to their paper, traditional 2D self-supervised frameworks like rotation and jigsaw puzzle and exemplar also worked very well in 3D medical images. The last one is Modelogenesis, posted in 2021. They collected lots of 3D medical images as unlabeled training dataset, and they used 3D image restoration as a proxy task. Modelogenesis show state-of-the-art performance in 3D medical image analysis. As an introduction, I have to introduce transformer as my encoder method. In 2017, Vaswani et al. Introduced transformer method in the paper named Attention is All You Need. Transformer showed great performance as an encoder, replacing traditional encoders like CNN and RNN or LSTM. However, this adaptation of transformer was limited to natural language process areas. It's hard to adapt transformer in computer vision area because it demanded tremendous computing resources. A paper from ICLR 2021 showed an answer to adapting transformer in computer vision area. The model named Vision Transformer solved computing resource problem by splitting input image as 16 by 16 small patches. Thanks to Vision Transformer, studies that using transformer in computer vision area widely is emerging. Medical image and analysis area are also adapting transformer in their models. A paper from Karimi et al. Posted in 2021 used transformer mechanism in 3D brain image segmentation. Two other fancy papers are TransUNet and VIT-VNet. They used both CNN and transformer in traditional UNet network named hybrid framework. The performance of these models outperforms traditional 2D and 3D UNet-based models. Medical Transformer, posted in 2021, is my base model which uses CNN Transformer hybrid encoder to train unlabeled straight 3D medical images with self-supervised learning method. This model works very well at one modality, but there exists some problems in adopting multimodal medical images. To solve this problem, I adopted domain-invariant adversarial learning in our base model. Recent adversarial learning methods have shown impressive results in domain adaptation tasks, transferring knowledge from the source domain to the target domain. In domain adversarial learning, the principle which uses GAN has been employed to ensure that the learned representations are domain confused. For instance, domain adversarial neural network DANN proposed a gradient reversal layer to ensure the similarity of feature distribution in the two domains. Universal model, posted in 2021, is a typical model that uses domain-invariant adversarial learning method. in medical self-supervised learning method for multimodality. This model used simple autoencoder framework with image restoration proxy task. Their method for multimodality is using MIAL module, which trains multimodal image representations with domain invariant adversarial learning method. My model is progressing in just a low level, so I introduced a simple and rough framework of my method. Two modality images, MRI and CT, are used as input images. These 3D images are separated into 2D slices with axial, sagittal, and coronal spaces. These slices to the images go through hybrid self-supervised learning encoder, which has CNN and transformer. I will additionally adopt multimodality invariant adversarial learning module in this encoder. Through that module, the encoder can train the generic representations of both MRI and CT images. In the future work, after reading a bunch of papers about domain adaptation and knowledge distillation, we have to reinforce our method. And I will think about a novel method to improve our model's raw generality. Also, I will think about how to solve the scale problem which our methods do not handle. And I will check if our proposed method worked in good performance. Thanks for hearing my representation. And here is the reference I used for this presentation.